Okay, so what do you need to know in regards to liver anatomically? You anatomically know 4 lobes, basically. Does that make sense? That's one. Second, what is the structure of the liver? The elementary building block of the liver is the liver lobule. And you need to know the anatomy of the liver lobule. Lobule looks like this. It's a hexagonal structure, more or less, right? And in the center of the lobule is a central vein, okay? And in the corners, you're going to have so-called portal triads. So you've got portal venial, portal arteriole, and bile ductal. The structures are called portal triads because there are 3 vessels there. Are we clear? Excellent. So let's talk about blood flow that happens in the lobule first. Okay? So now look at this. The portal arteriole and portal venial carry slightly different types of blood, right? So venial, in this case, carries deoxygenated blood. We're going to talk about the whole path for blood flow. Arteriole carries oxygenated, but turns out both of these bloods mix, and the blood enters the sinusoid. Okay, so this sinusoid here in the center, you see that? It's a capillary, it's a small blood vessel that is very, very permeable, and there's an active exchange between sinusoids and the hepatocytes that surround them. You with me? So oxygen, CO2, obviously, and also nutrients. So nutrients that are, we're gonna talk about where these nutrients are coming from. Don't worry, but nutrients from the sinusoid, from the blood in the sinusoid, enter hepatocytes. Hepatocytes convert them, process them, store them, whatever they need to do. So active exchange, and then the blood enters the central vein in the center of the lobule, right? And the central veins in each lobule, they all collect the blood that just went through sinusoids, and they merge into bigger and bigger and bigger veins. Are you following me? Until eventually they dump it, they merge into the hepatic vein, which dumps it into the vena cava. Okay? So let's talk about a little bit about the blood flow, which blood vessels supply the blood to the liver, and which blood vessels drain it. So to understand the whole process, we need to realize that there are 2 main players in this whole blood flow situation. You have the liver, well, 3 actually. Liver, intestines, right, and the heart. Because when there's blood, there's heart involved, okay? So let's think about the functions of these 3 organs. Heart pumps the blood. Clear? Intestines digest and then absorb nutrients. Clear? And what is the function of liver? The function of liver is to process these digested nutrients. Maybe, detoxify some of that stuff. So basically, this is your farm, and this is your food processing plant, so to say. So, your food processing plant definitely needs some blood that contains oxygen. So, heart will deliver oxygen-rich blood through the hepatic artery. Does that make sense? Okay. Of course, it's not like, it's not like a direct blood vessel that goes from the heart to the liver. It's a bit more complicated, but you get the gist, the idea. Now, intestines, they do get, a whole bunch of arteries going to them. It's not our primary interest. What our primary interest is the blood that leaves intestines. So, obviously, the blood that flows away from the organ has low oxygen content. So it's going to be veins, right? But particularly for intestines, the blood that drains from intestines not only contains low levels of oxygen, it contains high levels of nutrients because it absorbs all the nutrients, right? But interestingly, these nutrients, they don't go into the general circulation. You need to get farm products into the food processing plant, right? So you have, and that is one of the few situations when you have a vein going from one capillary system in the intestines to another capillary system in the liver. I'm deliberately hinting you on this. We already talked about a system where veins connect one bunch of capillaries to another bunch of capillaries. Do you remember that system? Yes. Hypothalamo-hypophyseal portal system. So this is your classic portal system. It's hepatic portal vein, okay? It's not a hepatic vein. It's important. There's a difference, right? So hepatic portal vein brings that nutrient-rich blood to the liver. Make sense? Vein branches into the small venules. This is the ultimate branch. Does that make sense? This portal venule is the ultimate smallest branch of the hepatic portal vein. And portal arteriole is the smallest branch of the hepatic artery. Everything mixes, gets processed, drains into the central vein, and then central veins, by merging, form just a hepatic vein. Does that make sense?
So, because the hepatic artery is sending oxygenated blood,
Mm-hmm.
so is the blood that's going through the hepatic vein still deoxygenated?
Oh, yes, of course.
So is it just the deoxygenated blood from the portal vein is more than the oxygenated that's in? If you're mixing the deoxygenated and oxygenated blood in the sinusoid,
Mm-hmm. Oxygenation will go down.
okay, so it's
still going to be sufficient for oxygen diffusion from the blood into the cells. It's going to be fine.
okay. So the blood in the hepatic vein isn't the mix of oxygenated and deoxygenated.
At this point, it's purely deoxygenated because cells in the lobule took all the oxygen out.
Oh, okay.
But importantly, this blood that goes in through the hepatic vein into the vena cava, it now contains, look, all the nutrients that were properly processed in the liver. Not just a bunch of amino acids, all right? For instance, you eat a lot of, you drink a lot of milk, which means a lot of lactose, which means not just glucose, but also another monosaccharide, galactose. Your cells can't really use it. So liver has to convert galactose into glucose. So cells can use glucose or store it, whatever. Does that make sense? Awesome. Okay, we got this. This is called enterohepatic circulation, and we'll get back to that idea a little bit later. Does that make sense? So, that's the blood flow. Now, the main contribution of the liver to the process of intestinal digestion is bile. So, you have two organs that deal with bile. It's the liver and gallbladder, right? So liver has 4 lobes, large right, smaller left, and then very small caudati and quadrati lobes. And they all produce bile, and the bile drains into the hepatic bile duct. Okay? Gallbladder is connected to the system via cystic duct. Does that make sense? Now, check this out. You see these 2 smaller ducts over here? It's basically left hepatic bile duct and right hepatic bile duct that go from corresponding. I just don't think it's particularly important. So when they merge, cystic and hepatic bile duct, they form main bile duct. Which enters the intestine. Okay? Kind of spoiling the story a little bit, just so I don't have to talk about it again. Pancreas releases the pancreatic juices through the same orifice. See, this part right here is called hepatopancreatic ampulla. So, why it is important? I killed the schematics of the regulation of digestive activities in the intestine. Remember we had this here? So when pancreas and gallbladder and liver are all stimulated together, look what happens. Pancreatic secretion and bile, they mix and they enter the intestine together. Does that make sense? Great. Now, let's talk. Say a few words about gallbladder and just forget about it. So gallbladder stores bile, right? It stores and concentrates it. Am I clear? It does not produce it, it just stores and concentrates it. And I already mentioned that secretin stimulates production of bile by the liver, but not too much, okay? So what actually serves as the main stimulus for the bile production? The answer is a little bit paradoxical. It's bile. So before we get to this concept when bile stimulates bile, we need to figure out what's in the bile. So bile contains bile salts, lecithin, bilirubin, and cholesterol. Okay? Now, I'm going to explain where these components are coming from. So let's start with this one, cholesterol. A lot of hormones, for instance, all adrenal hormones, all gonadal hormones, are cholesterol-based. They're lipid-soluble. Does that make sense? So you need to get rid of them. That's what liver does. It breaks down excessive hormones to cholesterol, and cholesterol is then dumped. Okay? Bilirubin. Your red blood cells. Your red blood cells get broken down from time to time. Does that make sense? And one of the components of that breakdown is heme. Now, heme is kind of toxic. So heme is broken into bilirubin. The main problem with the bilirubin is that it cannot be successfully released. Let me show you this. It's absolutely incredible. So heme is broken, metabolized to bilirubin. Okay? So usually things like that get excreted in the urine, right? The problem with bilirubin, it can't be excreted with the urine. I don't remember exactly. I think it binds to albumin, and it's impossible to filter it in kidney. So bilirubin then is excreted in a bile. And if you look, bile gets into the intestine, right? So first of all, bilirubin gives feces this brown color. Second, really important thing, and it's kind of cool. Bilirubin that's found in the bile serves as the food for intestinal bacteria. Okay, and they convert it to urobilinogen. It's not, we don't need it, just convert it into urobilinogen. Now, urobilinogen, and that's also remarkable, urobilinogen is absorbed in the intestines. Does that make sense? So urobilinogen goes back in the blood. However, check this out. Bilirubin cannot be filtered out from the blood. Urobilinogen can. Okay? So it is filtered out into the urine. And amber color of urine is because of urobilinogen. So sort of indirectly, bilirubin gives feces the brown color and indirectly gives your blood, gives your urine a amber color. Make sense? Lecithin and bile salts. What do? They are emulsifiers. Okay? One of the good examples of emulsification is when you wash a greasy pan. If you try to wash a greasy pan just with water, you will fail because grease is not water soluble. So what you add soap. Soap emulsifies the grease, the fats, into hydrophilic micelles. So both bile salts and lecithin, so to say, have hydrophilic head, okay, and hydrophobic tail. Okay, that makes sense? Now, when you have fat, bile salts and lecithin will just stick around, okay, extending the hydrophobic tails to the fat and hydrophilic heads outside. So they are emulsifying both lecithin and bile salts. They are emulsifying lipids. Does that make sense? Are we clear? Now, we come to that awesome part when you figure out how bile stimulates bile. It's actually very simple. I'm going to try and stick it over here. Okay, so look. Fat stimulates bile release from gallbladder, right? Bile ends up in the intestines. So far we good? Turns out your blood can easily absorb bile salts. Am I clear? Blood can absorb bile salts. Blood absorbs bile salts in the intestine and via hepatic portal vein delivers those bile salts to the liver. And they act on the liver to release bile, more bile. Does that make sense? You see this one here? So again, bile from gallbladder enters the intestine. Bile salts get picked up by the blood, delivered by hepatic portal vein to the liver. Themselves, bile salts themselves stimulate liver to make more bile. That bile enters the intestine. It's a typical positive feedback loop, surprisingly. But then here's the thing, not all bile salts get picked up. So when digestion is over and there's no stimulus, there's no fat in the intestine, none of that initial stimulus persists. So yeah, your liver keeps making bile, but the whole thing is kind of winds down. Do you need the bile in the intestine? Probably not. So what happens? The sphincter at hepatopancreatic ampulla closes. bile flows back in the gallbladder, and it is stored in a gallbladder. Does that make sense?
Does it flow backwards?
Kind of this way, yeah.
Okay.
Yeah. So it accumulates in a gallbladder. Now, this is an interesting clinical update here. We already figured that introduction of food, introduction of chyme in the intestine does not really stimulate the release of bile by the liver. Does that make sense? So, and we all already figured, check this out, that a fat requires emulsification, right? So without bile, you can't really digest fat. By the way, because of this, people who are in the liver failure, one of the problems that they have is that they have really, really hard times to digest fatty food. But not only this, imagine that somebody undergoes cholecystectomy. Sorry, it's so basically removal.
It's a mouthful.
Yeah, removal of the gallbladder. Now you don't have this reserve, this storage of bile. So if you eat something fatty, you have nothing to eventually it will pick up, but it's going to be a while. Does that make sense? And fat, basically, if hypothetically you would take a person without gallbladder, with healthy liver, without gallbladder, and feed them, I don't know, 5 lamb chops, they're going to have what's called steatorrhea. Because without emulsification, fat won't be absorbed, it will remain in the intestine, and that will lead to a very unpleasant form of diarrhea, which is fatty diarrhea. Okay, very interesting situation. Now, I'm going to give you some really fun clinical updates here. So first, what is liver cirrhosis? Liver can take only so much impact, so to say, you know? So, liver cirrhosis is inflammation of the liver. Remember, we talked about inflammation before on multiple occasions. And I think in AP1 I mentioned that inflammation results in the repair, and that repair is usually connective tissue. It's not liver. So functional hepatocytes are replaced by connective tissue. So in addition to a lot of things, hepatocytes are the cells that produce bile that drains into these bile ductils. So you have a problem with the fat digestion, first of all. But also, you have a problem with the excretion of steroid hormones. Does that make sense? I mean, there are different stages of cirrhosis, but people who are in not end-stage liver disease, but like very advanced liver disease, liver failure, they will not be able to excrete steroid hormones. And for males, it's a particular problem because in liver, testosterone is converted first in estrogen, which is then excreted. But if males fail to excrete estrogen, estrogen levels start to rise, and they start to develop secondary sexual characteristics of females, which was greatly summed up by one of my students who actually worked in some medical facility taking care of people, among them were alcoholics. And she said something akin to, "Now I understand why my drunks grow boobies." And that is actually true. They develop gynecomastia, one of the signs, you know.
Yeah.
That makes sense?
Yep.
And finally, why, people take out gallbladder. Sometimes there are some weird situations, like rare situations when there's increased motility, but most commonly, of course, it's gallstones, right? So what is the gallstone? Mostly in people who don't move enough or eat a pouring amount of fatty food, right? Because if you eat a lot of fat, a lot of bile goes into the gallbladder, a lot of concentration, that's important. But if you sit around and you don't move a lot, then if you concentrate a liquid, it will increase the concentration of stuff in there, including cholesterol. So gallstones are usually pretty soft. They're formed mostly of cholesterol, bile salts, of course. But then they will block the cystic duct. And when gallbladder tries to pass bile, and the duct is blocked, it's really painful. That makes sense. Now, my favorite story regarding gallbladder is, I always ask students to guess what was the size of the largest gallstone extracted from a person, so that person survived after that. Single gallstone. Any guesses? Come on.
2 pounds.
You are underestimating how ignorant people can be. The largest gallstone was extracted from a British woman. She survived, like she lived after that. And it weighed 14 pounds. It was the size of a watermelon. I don't know how you don't notice it, but nevertheless, you're processing.
Did your gallbladder explode?
No,
Like,
it stretches.
that
It
much?
stretches, yeah, it stretches. Turns out it stretches that much. Yeah, it was the largest gallstone. Yeah, it was probably very painful to walk around with it. As far as I remember, the patient was obese also. Okay. Make sense?
Kind of.
Kind of, yeah, I know. Kind of. Okay.